Can we go to the first slide, please? There we go. Thank you. Good morning. I would like to tell you about how dust can move between these satellites. And my story will actually start at the moon, because the best dust environment understanding that we have on a featherless body is the moon, since the LODI mission was completed there. I will tell you what I expect at Phobos and Deimos, how the dust actually will form possibly a whole torus around Mars, and why that is a hazard you should worry about. All airless bodies, or even the ones with air, of course, are continuously bombarded. At Earth, you are very familiar with meteor showers. You go out and see the shooting stars. It's very pretty, and we know about it for centuries. And of course, small particles that were released from their sources, be that an asteroid or a comet, eventually decouple from their sources because of the perturbations from other planets and radiation pressure. And we categorize them as the sporadic meteorites. These are the little particles that forgot their sources, and they come at all times at all places. But it's not quite uniform. People who do radars and optical observations identify various apparent sources in the sky where more particles seems to come. So if you go to the moon, instead of shooting stars, of course, you raise ejecta clouds. There is no one to slow you down. There is nowhere to burn up. You directly hit the surface. You raise clouds of dust that typically rise up with a few tens, maybe even 100 meters per sec. The ones that are faster can possibly even escape. And if you have a spacecraft like LODI around the moon with a dust instrument circling around and around, you see these clouds as you fly through this region. And this is the entire data set from LODI. This is a function of time. It was a very short mission. We started in November 2013, finished in April. These are the large particles, bigger than 0.7 micron in radius. These are the small ones. We were continuously recording hits time to time. You see that the number of hits skyrocketed. And actually that peak was persistent for days as we flew over and over and over the region where the meteorite stream was hitting the surface. You can then combine this and says, on average, there is an ejecta cloud persistent around the moon. Every little particle has a short lifetime, maybe a 10-minute flight time. Most of them would immediately fall back down. But continuously there is an ejecta cloud, and the ejecta cloud is non-uniform. Black actually here means that we could not make measurements because of the orbital dynamics of the spacecraft, or because the instrument cannot possibly look into the sun, which on these plots is to the left. But on average, here is the ejecta cloud. We are ramming in, the ram direction is the one where the highest impact speed are expected from the small amount of retrograde particles that could possibly hit that part of the moon with up to 60 kilometers per second. What we noticed, of course, that as time goes on, this cloud is breathing. It's alive. It's not constant. For example, if you have these sources, the apparent sources, the helion, anti-helion, and so forth, as the moon goes around the Earth, there is a kilometer per sec speed variation going upstream and downstream into the average incoming particles that would rise more and less clouds, ejecta clouds over the surface. So there is a monthly variation. Certainly there is an annual variation because the helion anti-helion sources trade off as the year goes by. So we learned a lot around the moon, and we certainly learned that yes, during intense periods where there's a whole lot of incoming, like during the Geminids, every time we flew around that region, the number of impacts are skyrocketing, and there are intense periods where what we call bursts, that instead of a hit per minute, we record tens or even 100 hits per minute. And we do that over that region, orbit by orbit by orbit. And then if you do this carefully, you could actually read off the radiant where this incoming was, and then you can get into lovely arguments about the ground-based observer, because so it appears that at the moon, we noticed a meteor stream that was no record on the ground. And then we'll figure out what it means.
Please, can you get closer to the microphone?
I am sorry. All right. Thank you. So maybe there is yet another stream, and we're going to examine it more closely. And then you would argue, wait a minute, Phobos and Deimos, they are continuously bombarded. Tell me what happens there. And I have to tell you, I cannot really tell you what it is. That is one of your lovely SKGs, because we have no radar on the ground. We have no observers on the ground. We don't have centuries-old records of what's incoming. Nevertheless, of course, I'm good in making up stories. So here it is. Let's try to figure out, based on my measurements and based on the few spacecraft that actually, cross the solar system, let's try to figure out what's happening. Of course, I can launch particles and figure out, first of all, Phobos and Deimos are tiny compared to the moon. The escape speeds are tiny. Most of the ejecta will, in fact, escape, not fall back. If you are escaping, I can, turn on the forces, integrate F equals ma, and tell you as a function of radius or mass, what will be your life history. If you are tiny, electromagnetic forces, the V cross B force from the solar wind will sweep you away. You're becoming like a pickup ion that we call in the business. You'll be a pickup nanodust, and off you go. If you are a little bigger, radiation pressure is a conservative force. Your energy will be conserved. That's good enough. Your angular momentum will be continuously lost. Your eccentricity is growing. You will eventually hit Mars. You will be deposited into the atmosphere. If you are getting bigger and bigger, then you would recollide with the source body. So imagine that we're going to run a billion, thousands and thousands of particles and build up the torus that is ejected from Deimos or ejected from Phobos. The typical densities from the Deimos cloud is 10 to the minus 4. And actually, it's not really a Deimos cloud. It's Deimos' contribution to the dust torus around Mars. Depending on which is your home, Phobos and Deimos, the characteristic sized particle that lives the longest from Deimos is about 15 micron. From Phobos is about 50 micron. You generate a lot less 50 micron than 15 micron size particles. So in fact, Deimos is dominating the dust torus around Mars. There is more dust from Deimos than it is from Phobos. And then it's the interesting dynamics. If the sun is up here, through the lifetime of a particle, you would actually not say uniform. This is the side, this is the top down. You're looking down on the system. You're looking sideways from the two projections. And this actually is the obliquity of Mars combined with the effect of radiation pressure. Some of that dust that dominates the torus, originating from Deimos, will actually land on Phobos. And we could calculate that, at least based on the assumptions we are making. And this is the map of the dust deposition rate. Most of it actually will catch up with Phobos and will be deposited on the trailing side of the moon. And we are delivering about 1 to 2 kilograms of Phobos dust to Deimos every day. Yes, you are doing the math in your head, I can see. Would that in the lifetime of the solar system, would Phobos vanish? You're fine. You're off by many orders of magnitude. So if I were to carefully arrange and forget about the fact that, an incoming particle, even though the relative speeds are sub-kilometer per sec, would also generate ejecta. Phobos is continuously bombarded. It will lose ejecta from the surface. If I forgot all about this, the accumulation rate, if you were to do spectroscopy, is about 100 nanometer of new material being deposited every year. So, some people had this wonderful idea. We could learn a lot. Take LADI, beef it up a little, put it over to Mars, and try to do the same measurements. That proposal from Ames didn't quite made it yet. Eventually it might. And of course, then one could argue that, wait a minute, at least based on my best knowledge, I can tell you the impact rates. And the impact rates are not that different than around the moon. This is a perfectly executable measurement. We could do this. You don't have to invent new technology. You don't have to invent new devices. I am not arguing that one should fly a single dust instrument, though that would be a good deal. But you could certainly do this measurement among many other things that our friend doing spectroscopy or other things should do. This would be, for example, typically, I imagine you would fly around Mars, and once in a while you will have encounters with Phobos and Deimos. This would be then the Phobos torus, then the Deimos torus, and this is the impact rate and the number of impacts that we could predict orbit by orbit by orbit. So, I am here to conclude. There is a way to use airless bodies as dust detectors. They have a tremendous magnification. An incoming particle will generate, an incoming typically 100 micron particle will generate 10 to the 3 or many hundreds times more outgoing particles in a much smaller size range, typically submicron. So there's an enormous number of them. It's very easy to detect if we figure out how to actually translate incoming to outgoing ejecta clouds. Certainly at the moon, I can testify that the lunar dust cloud quickly responds to changes in the meteorite flux. We could learn and add that to our NASA engineering models. If you know this, the meteorite engineering model, MEM, or the European MEM, there is a way to include, hopefully, the lunar dust measurements into our understanding to make better predictions for the incoming large particles. This process must be at work at all airless bodies. Let it be an asteroid, Phobos and Deimos, wherever you go. If you are exposed, you are generating secondary particles. Because of the small size of Phobos and Deimos and because of their proximity to Mars, they will not hang on to their cloud, they will share it and form a dust torus. All HST and optical observations who try to do this measurement is difficult because the optical depth is very, very small, 10 to the -8, but an in situ dust instrument would have no problem detecting the cloud. And as missing, the Deimos to Phobos dust transfer rate is about 1 to 2 kilograms per day. And dust is a hazard you should learn about. It's a hazard to crew and mission one day to Mars. Thank you.
Go ahead, Jim.
Jim Head, Brown University. So, in reference to your last point, as a co-investigator on the Phobos missions, one of the prevailing hypotheses for the failure of one of the two Phobos missions, the Soviet Phobos missions, was in fact dust tourist and dust and impacts, etc. What do you think about that hypothesis?
So there,
as you know,
I was much younger. This is the Phobos. So, no. This is okay. There is a piece of data that we are struggling ever since. That's called the Phobos. Oh, the Phobos Event. The Phobos Event. This is the spacecraft get lost, and when you when you went through the torus, the magnetometer had a little blip, and we are arguing about it ever since. And we try to put dust torus, and Andrew will give you maybe a plasma torus or something. Something happened there, which is the only in situ indication we have today about the dust torus. It is possible that it knocked out the spacecraft. There could be many other reasons for spacecraft failure. But there is this one piece from, and I think it was the early 80s, the Phobos Event, that I carry in my head ever since. One day, we'll figure it out.
I was in high school at the time.
Mihaly, in the case of the moon, your main source of impactor seems to be the Geminids, right?
The main source of hiccup, but we had an average rate of about a hit per minute, regardless. And in fact, a lot of the analysis was done in a period of time when we are looking for the yearly changes in the sporadic background is the early part of the year, January, February, March, when we had no streams.
Okay.
But certainly the streams show up.
Let's talk about this offline and try to figure out what might be the main source into the Mars system.
Fascinating story. Coming back to some of the things we were talking about yesterday, though, about the origin of Phobos and Deimos, you discuss how dust can move between these, and in particular, one direction from Deimos to Phobos. But we still have a lot of fine particles on Deimos, and they look very similar to some of the particles on Phobos. But the origin of those fine particles, the regolith of Deimos, we still have to address in terms of the origin context. So how do we get our arms around that part of it?
So the statement that the bulk of the material is transferred from Deimos to Phobos is for the characteristic long-lived particles that make up the bulk of the torus. The tiny ones that live very short, if they are ejected from Phobos, they can certainly make their way to Deimos. There is some level of reciprocity. The calculation, the kilogram per day dust transfer rate, is for the 15 and 50 micron characteristic size particles that are the longest lived in the torus. So what you're asking is more homework. We could certainly start looking into how much Phobos dust is ending up on Deimos. That's doable. And then, of course, I'm out of my league. I cannot help you with the origin of these bodies.
Time?
Okay, one last question.
Sorry. On the deposition map that you showed before, I don't know if you can flip to it real quick. The area that, yeah, up there, is that, no part of that map is zero, correct? There's always some deposition even in that purple to gray.
This is about 90%.
Yeah, no, I'm asking the opposite. On the minimum,
Oh.
is there any part that's zero? And if you're getting depositions of 100 nanometers per year, wouldn't one conclude that basically the surface of Phobos, we're seeing the material that is the surface of Deimos, obscuring spectroscopically all of our measurements?
So I have to be careful because what happens, of course, depending on which surface element on Phobos you are looking at, it's quite likely, and I have it in the data files, that the impact, the incoming speed, of course, is very different. If you come in at high speed, then you are, of course, generating a lot of secondary ejecta,
Right.
and you are gardening the original surface. So to answer your question, maybe is the best I can give you.
Okay.
At some point, we're going to have to think it through. How much of the original, if you are a spectroscopist that you are, then how much of the original material could possibly still preserve through the millions of years? The answer is
Not clear.
not obvious to me.
Thank you.
Okay, thank you.